Okay, all right. Good evening to you. Let's get started. Well, we're going through the same thing again today. But that's what I said. What foundations are about. You just on repeat till you get a firm foundation and hopefully intuitive understanding of what we're doing here. Okay, all right. So the last day we're discussing the sampling distribution for the resultant essential limit theorem for quantitative type data, mean type data. Today it'll be the same idea for proportion type data. But let's just review what we went through from the last day and then get into it from the point of view of a sample proportion. We've learned that many variables in nature take on the shape of the normal distribution. And again, we discussed the characteristics of that and you need to get very familiar with that curve because as it should be clear to you, that is what we reason around throughout the remaining of the course to develop our ability in statistical inference. We went through a poll question on IQs. And so, as I said to you the last day, it's very important to understand we're in the world of the population, where everything is known and where we know the population, say, mean value or mean IQ for the IQ example. So take this as IQs. In that the average IQ is 100 and the standard deviation, sigma, is equal to 15. And if we assume a normal distribution of values, then we can mark off one standard deviation, two standard deviations in either direction, at least roughly. We know that the mean is in the middle of the curve and that this is one standard deviation above and two standard deviations above. And one standard deviation below, one standard deviation, two standard deviations below. Yes, you need to understand the characteristics of the normal distribution and the empirical rules for the normal distribution. It's symmetric, and 68% of values are within one standard deviation, 95% of values are within two. So what is that saying to us? Basically, what the takeaway from that is that for individual measurements that follow the normal distribution, 95% of those values, at least approximately, are expected to be within two standard deviations of the mean. We went from there into the constructing and reasoning with what's called the sampling distribution. And it's basically a distribution of sample statistics based on the same sample size. And so what we've found is that through simulations, that if you take a population of values, IQ values in this case, with this mean and this standard deviation, and you were to take sample size of, say, 100, again, don't confuse that 100 with this 100. This is the sample size you take. That the distribution of all the sample means that you could calculate based on sample size of 100, if you were to repeatedly take sample size of 100 and get sample means over and over again, that the distribution of those sample means would be centered at the population mean of 100. It will take on the shape of the normal distribution. It'll have a variability, obviously, in the sample means, and we measure that with what we call the standard error. And the standard error is, write it like this for shorthand, the standard error of the sample mean is equal to the population standard deviation, sigma, over the square root of n. So variability in the reasonable measurements come into play. In how close on average you expect your sample mean to be the population mean, because that's what standard error is measuring. What's the fuel underneath the hood? What's driving your sample mean towards the population mean is the sample size, either from this side, from the left of it, or to the right of it. And so we calculate that out. In this case, it's 15 over the square root of 100, and it's 15 over 10 is equal to 1.5. And so the result of the essential limit theorem states that the distribution of sample means based on a particular sample size will take the shape of the normal distribution. And this is a measure of variability of the sample means around the population mean. So this is 101.5, this is 103, this is 98.5, and this is 97. Okay, all right. For some of you, yeah, it can be a bit of a wall or a mountain climb to go from this concept to this concept. What we have here is a result, yes, and that's what we want to go forward with. And it's a very powerful result. It's what the universe has given us. Again, this was discovered. We didn't come up with this. It was discovered. Francis Galton was the main guy who really understood its importance. The quote I gave you there a couple of lectures ago from him. Extreme curiosity. Yeah, many mathematicians along with him said he was backward mathematically, but that's all relative. But he had extreme curiosity, creativity, and persistence. And it's people like that that actually make a difference in the world. Understood its importance through collecting data over many years. That we can now do inference. We can go from sample to population, knowing that the distribution of the sample means take on this shape. That's what we'll be going with from today on, and reasoning around what we call the sampling distribution model. All right. So the universe gives us something to work with, but that doesn't mean our job is easy. We'll come up with two approaches to making use of this result. One we've hit upon already, a confidence interval, where we try to capture the population mean value within the confidence interval. And then the other approach will be hypothesis testing. You'll get your head around this if you commit to it, even if it is a challenging concept on the mind, because we're just looking at it from the theoretical point of view. It's when the population mean, which you start in the next day, becomes a question mark. That's where statistical thinking and reasoning comes into play. And that's where it should get more interesting. Because at the end of the day, in the point of view of the population, we know everything. That's not our point of view. We don't have full knowledge. We don't know what the population mean value is. We only have a sample mean from one sample size to work with, and this result. And we try to play our cards as best we can. See what we can come up with as a way of reasoning with this result through statistical inference, confidence intervals, and hypothesis testing. So yes, so for some of you, it may be useful. I kind of went through it pretty quickly, but that's it. Well, that's the end result. And okay, just to focus in on just like I did up here, just what it's telling us is that no matter whatever the value of the population mean is, I'm setting it here to 100, but whatever the value is, at least approximately, according to the result of the central limit theorem, 95% of, this should be 97. That 95% of sample means are expected to be within 2 standard errors of the population mean. So that's the takeaway from this. And that's what the result tells us. And then that's what we work with. And because of that knowledge from this result, we can calculate probabilities like in hypothesis testing p-values in order to make decisions about the values of population parameters, how effective a drug is on an entire population. The tool here could be, where is it? Yeah, it could be of some use. Again, I hope to find something a bit better, because the idea here, and if you have time, you might want to see it constructed. So this is just a sample of 5 values from that distribution with a mean of 16 and a standard deviation of 5. Add up the values divided by sample size. The sample mean fell in this interval here, so we create a little block. And so you do it again, and you might have fun saying, where's it going to land? Because the key thing I wanted you to key into here, from your intuition point of view, is that sample means vary from sample to sample. And the larger the sample size, the closer you expect your sample mean to be to the population mean. That should be intuitive as well. More information of quality data, you'd expect your sample mean to be closer to that population mean. But this could be useful to you to just see it stacking up. You see the sample means are varying around the population mean of 16, marked here. If you have time, you can build it up slowly if you need that sort of thing. But again, at the end of the day, it's the result that matters. And the key thing to take from the result is that whatever the population mean value is, 95% of sample means will fall within 2 standard errors of that value, at least approximately. We want to work with that result as best we can with confidence intervals and hypothesis testing. And that becomes our model in hypothesis testing, becomes our model in confidence intervals as well. And I will be repeating throughout the course a famous quote from a statistician, famous to statisticians anyway, from George Box. All models are wrong, some are useful. Why is that? Because we don't know. We don't have full knowledge, but we pursue full knowledge, and that's what's the power of the scientific method. We don't stop at belief. We pursue knowledge. Paradoxically, we have to reason uncertainty to try and get as close to truth as possible, or full knowledge, or get as close to that population parameter as we possibly can. And that's the power of the scientific method over other ways of reasoning with truth, that we don't stop at belief, try to get as close to the truth as possible. And we do that through reasoning with doubt, measuring that doubt or uncertainty with probability. What I'm talking about is what can a sample mean? Tell us about a population parameter. And again, that population size does not matter. It could be a million, a billion, a trillion. It's all sample size driven. Let's do it again for proportions. Okay, all right. So we'll be analyzing two types of data, categorical and quantitative. That was made clear from the start. And so today we'll visualizing and summarizing sample statistics, sample proportions. A sample proportion or percentage is an estimate of a population proportion. The statistic we're interested here is a sample proportion as an estimate of the population proportion. Yes, no data, election type data. But whatever type of data has a yes, no answer to it. That type of categorical data, which we'll be analyzing. So you might be interested in the proportion of population who would vote for a particular candidate in a national election. And so, yes, the sample proportion is simply the number of people in the sample who say they will vote for the candidate over the sample size. Okay, so that's your sample statistic. We're learning to understand how to reason with sample proportions from sample to sample. Again, it's sampling variation is what we call that. Reasoning with the variation in sample statistics from sample to sample. You all agree that sample statistics vary from sample to sample. Here, yes, the samples are of different size. We're focusing more on the idea of samples of the same size and how they vary in the ordered shape of the normal distribution around the population parameter. In this case, the population proportion of people who would vote for Biden or Trump in 2020. Sample proportions for Biden and Trump varied to some degree from poll to poll. However, the average, at least for Biden, and this is national polls, the Biden was not too far from the outcome. But with Trump, it was a little off. And that's, I think, one of the major factors is that not people didn't want to say they were going to vote for Trump, or a number of people. And so that would show the estimates off. But for Biden, it was pretty close to the outcome. And that's what we're really getting at, is that the average of all the sample proportions, at least in theory, should be the outcome, the population proportion. So elections are that unique example where we can actually see afterwards what the value actually was. Again, for Trump versus Harris, again, they vary, but they were much tighter, quite consistent. So there wasn't a whole lot of variation there from poll to poll in terms of the sample proportions. And this time, both were pretty close. Again, this is pretty close and not as close, but closer than in 2020 for Trump. Okay. All right. So again, samples proportions will vary from sample to sample, but the average of them all should be equal to, at least in theory, the outcome or the population proportion for Harris and Trump. Okay. All right. As I said, I introduced this graph the last day, and it is very important. I'm just trying to navigate you through this subject as best I can and make you aware of the pitfalls. And I think one of the pitfalls in general is not separating the thinking. Here we're right now we're in probability theory. Theorem is called the central limit theorem. It is a core theorem in probability, but it's the heart and soul of what makes statistical inference work. And so, yes, again, to be clear, now we're thinking about population proportions, and we're going to assume or say we know a value for the population proportion. Obviously, we don't, but we're assuming we do. We're in the world of the population, and that's in the world of 100% knowledge. And so we're going to be saying, well, what if P is equal to a particular value? I'm going to introduce it with the coin toss. And it does work. And I use it for the hypothesis testing too, the coin toss analogy, where P is equal to 0.5. A coin is considered fair. P, the population proportion of, say, heads you would expect to get, will be equal to 0.5 if the coin is fair. And then imagine tossing a coin 100 times and doing that many, many times. We'll do it through simulation and calculating out what we call the sample proportion, P hat, the proportion of heads you get in a sample of 100 coin tosses. You expect 50, but what you expect and what you get, it can be two different things. And as I said the last day, that's a big part of the reasoning of hypothesis testing. What we expect, given the assumptions in the null hypothesis, say the coin is fair, and you toss a coin 100 times, you'd expect 50 heads or proportion of heads to be 0.5. But what you might get, you will get a sample proportion that will vary around that value. But if it varies too far from that value, it's indicative that your coin may not be fair. if you get a proportion of heads, it's just unusual to occur from 100 coin tosses. Given the coin is fair, we have to make a decision of whether do we stick with the null that the coin is fair, or do we reject that null? And that's the core reasoning of hypothesis testing that we'll be getting into after the midterm. So that's it. We're still here from this point of view. Imagine again a coin toss analogy, tossing coin 100 times over and over again, looking at the distribution of the sample proportion of heads, and the p hat is the symbol for the sample proportion of heads. And again, the next day after our midterm, our review and the midterm, we'll be starting to look from here to here, where we only have partial knowledge. We only have a sample from the population and a sample estimate, sample proportion, say, as an estimate of the population proportion, and that becomes a question mark, and that's statistical inference. And that's reasoning and measuring and dealing with uncertainty, because the reality is we don't know the population value. We only have an estimate of it from a sample. And so we have to make inferences from the sample to the population to make decisions about the value of the population proportion or population mean. Okay, and that's statistical inference, statistical analysis. For today, we're still here, and then we'll turn the ship around and look from the point of view of the sample to the population, where these become unknowns. Okay, so just again, using the coin toss analogy, it does work well. You toss a coin, fair coin repeatedly, what is the proportion of heads you'd expect to obtain? All right, so we can be thought of as a question regarding a population proportion, where the population proportion is equal to 0.5 if the coin is a fair coin. And so, yeah, we can think of that value as a population proportion value. And we're assuming we know it's 0.5 because we're assuming the coin is fair. And so our sample proportion is the proportion of heads we'd obtain from a particular number of tosses. So we've seen this already. The concept of probability and understanding probability, which is important going forward too, because a p-value is a probability. In that probability is what is happening in the long run. And this is important too to understand for confidence intervals, to understand conceptually what we mean by a confidence interval. What would you expect to see in the long run when we're reasoning with a confidence interval? And so the idea is if the coin is fair and you toss it enough times, if it's a fair coin, the proportion of heads should converge at 2.5. Again, it should be intuitive. Yes, you'd expect 50 heads. You're more likely not going to get it. You might get it on one simulation or more than one simulation of the coin toss. More like, you're going to get values in and around 50 heads from tossing a coin 100 times. So yes, sample proportions vary from sample to sample, but they take on that familiar shape of the normal distribution. Okay, so this is the simulation. And if you have some computer coding skills, you could try it out for yourself. But I'm trying to get you to do it through the coin toss simulation. So that's the idea of it. Part of homework 5 has you toss the coin another 300 times, but do more than that if you can, because I'm asking you to calculate the proportion of heads. I can't remember the details exactly, but I'm trying to get you to create a histogram to see does it start to take on this shape. But you just might not have enough coin tosses done to be able to for this shape to emerge. And what I mean is that the histogram from your experiment of coin tossing may not take on the shape because you may not have enough sample proportions in your histogram for the histogram to come forth with the shape that is the theoretical result represented by the curve. In other words, I'm saying is that I did 10,000 simulations. 1,000 may be enough, but I did 10,000 simulations to make sure I had enough of tossing a coin 100 times and each time getting the sample proportion of heads. Again, we can see that the distribution of those 10,000 sample proportion of heads is at least approximately normally distributed if it's centered at the 0.5. And the only thing left is the measure of variability of those sample proportions around the 0.5. That's what we call the standard error. So we'll look at that calculation in a minute for proportions. It's a different calculation than standard error for means because we're dealing with yes-no data, not quantitative data. Okay, all right, so you do it 100 times. We see that we expect at least approximately 95% of sample proportion of heads to fall between 0.4 and 0.6, or between 40 and 60 heads. That's if it's a fair coin. And so let's take it to a 400. Toss it 400 times. Again, you would expect your sample proportion of heads from your tossing of 400 coins to be closer to the 0.5 than when you only toss it 100 times. And that, again, should be intuition. And that, again, the key idea here in this course is to appeal to your intuition to understand this stuff. And so we do see it's a narrower distribution. When you toss a coin repeatedly 400 times and calculate the sample proportion of heads you get each time, the distribution, again, of those sample proportions stacked up in a histogram are centered at the 0.5, at least approximately take on the shape of the normal distribution. And now this time, 95% of those sample proportion heads will be between 0.45 and 0.55. All right, so how do we calculate that measure of variability there? What I'm saying here is that basically in this case, because if you know the empirical rules for the normal distribution, that the standard error is equal to 0.05, because basically two standard errors below 0.5 is 0.4 and two standard errors above 0.5 is 0.6. So the standard error in that case is 0.05. In this case, it's 0.025. All right, so how do we calculate that? As I said, we are in the world of theory, and where we're assuming we know the population proportion, and we're assuming if it's a fair coin, that P is equal to 0.5. And so when you're calculating out the standard error, which measures the variability in sample proportions around the assumed value for the population proportion of 0.5, this is how you do it in theory. It is the square root of the population proportion, in this case 0.5, times 1 minus 0.5 over the sample size. Not important where that came from. It's from the binomial distribution. There are many probability distributions in probability. It came from the binomial. Binomial is a success failure distribution, where the outcomes are, say, head and tail. It doesn't matter. Just be clear, because it can be a point of confusion. And I'll map this out as we get into statistical inference, separating, categorical and quantitative, and standard error calculation for categorical versus quantitative. This is how you calculated out the standard error for sample proportions, where it was sigma, the standard population standard deviation, over the square root of sample size for sample means. Okay, so don't get confused from that. There's two different ways of calculating standard error. This is yes, no type data, ones and zero type data, yes, no type data. Yeah, the calculation is different. But what's driving it here, again, primarily, driving the accuracy of your sample proportion, meaning how close it's going to be or expected to be to the population proportion, is the sample size. It's on the bottom of the formula. It's the fuel underneath the hood, driving that sample proportion from the left to the right towards the population proportion. All right, when we get the confidence intervals next, we'll see how this changes. We'll be using our sample proportion from our one sample in there to calculate, and not using the population proportion. Why? Because we don't know the population proportion from the point of view of the sample to the population. Okay, but anyway, that's how we calculate it out. Again, to be clear, the standard error is very similar type of measurement as the standard deviation. It's a measure of variability. But in this case, the measure of variability of sample statistics around the population parameter, where the standard deviation is a measure of variability of individual data values, like height, around, say, the population mean for quantitative data. And so don't get confused from that. Some textbooks use standard deviation here, at least from talking about it from the point of view of theory. And we are in the world of theory right now. Don't get confused on that. And that's why I stick with standard error, even though we are in theory, stick with the term standard error. Because when we get to statistical inference, it's called standard error anyway, and it just can cause a confusion. So be clear on what it's measuring, as opposed to what the standard deviation is measuring. And so again, the larger the sample size, the smaller this value will be. Therefore, for the coin toss example, toss a coin 100 times, you're assuming P is equal to 0.5. You saw how we calculate the standard error is the square root of P by 1 minus P over the sample size. And so 0.5 by 1 minus 0.5, you calculate that out, divide by 100, and get the square root of that. All of that is 0.025. And then the square root of that is equal to 0.05. Okay. And then for tossing a coin 400 times, same idea, but we're just putting 400 on the bottom of the formula here. Sample size is 400. And then all of this, it becomes 0.000625, and the square root of that is 0.0025. It's the result we want to reason around. The calculations are pretty straightforward. It's the reasoning is challenging of statistical inference. This is the card we're playing with. This is the result that we're going to reason around after the midterm. And so there is a different sampling distribution model. That's what it's called. for each sample size used. In this case, the sample size is 100 coin tosses, and then the sample size is 400 coin tosses. In this one here, we see it for this 400 coin tosses, a narrower distribution. We'd expect our sample proportion in this case to be closer to the population proportion, as opposed to over here. It may not be the case. May toss a coin 400 times, and we get a sample proportion that's out here in the tails. We may toss it only 100 times. We might get one right beside it, but you'd expect to get a sample proportion closer to the 0.5 based on 400 coin tosses versus 100 coin tosses. Okay, so that is the central limit theorem for sample proportions. But again, it's the same idea for all sample statistics. The distribution of sample proportions based on a particular sample size follow normal distribution, at least approximately, and is centered at the population proportions. So in theory, the mean of all possible sample proportions based on a particular sample size is the population proportion. Okay, so however, this result is only true if the data collected adheres to the necessary assumptions and sample size conditions for analysis. Now, I've decided semester before last not to get into the sample size condition. It's described for both sample means and sample proportions in the textbook. Again, I don't want to distract too much with technicalities. Some professors might not agree with me, but if you I know from experience being in the trenches for 15 years, if I get bogged down in technicalities and like the T distribution coming up, it's just going to blow your minds. And that defeats the purpose here. The purpose is to get a sense of the reasoning, understanding of the reasoning. And you don't want to leave a course. Go down those roads. I feel it. I've felt it. Get into the technicalities to be technically correct. And then it just blows your mind and it defeats the whole purpose. So again, it's a technicality about the sample size needs to be of a particular size for that result to be valid, the result of the central limit theorem for both proportions and means. And it's different sample size condition for sample means versus sample proportions. But again, read about that. I just want to focus on the core reasoning without getting bogged down in any technicalities in a reasoning course like this. You have enough to get your head around without getting bogged down in technicalities. You just lose people, and that defeats the purpose. Okay, but a random sample, it should ensure independence. Independence is the core assumption, and we'll talk about it more practically from real examples, what we mean by that. We've discussed what independence means from a probability point of view, but we'll discuss it from a more practical point of view when we get to analysis. It is generally believed that nearsightedness affects 12% of all children. Take that as if it is the population parameter value or population proportion, 0.12. A school district has registered 170 incoming kindergarten children. So can we apply the central limit theorem to describing the sampling distribution model for the sample proportion of children who are nearsighted? Now, there is the sample size condition I mentioned that I'm not getting into, and that's the question is it would be alluding to that too. And you can look at how we calculate that out, and the sample size is large enough. You can look at the textbook for that. The key assumption is independence. The probability that a child is nearsighted in your sample should be independent of whether or not the other children are nearsighted. Is that a fair enough assumption to make, that independence in nearsightedness in your sample? Yes. Why is that? Yeah. It's common sense. Yeah, they're going to be independent measurement from child to child, unless there's twins or that or whole families in there. But otherwise, it's a fair enough assumption to make. Again, we'll talk more about real world examples about thinking about independence when we get more into real world data. Okay, so sketch and clearly label the sampling distribution model based on the 68, 95, and the 99.7 rule. Okay, and then how many of the incoming students might the school expect to be nearsighted? Before we look at the solution that's on the next page, how would you go about being able to sketch this? What do we need to calculate out to be able to sketch out this model, the sampling distribution model, the normal curve? What do we need to calculate? What's the key thing we need to calculate? Yeah, get the standard error. So the standard error enables us to construct this thing. And then we learn how to reason around it. And this is oftentimes how it's written more mathematically. According to the result of the central limit theorem, we can assume that the sampling distribution of the sample proportions of children that are nearsighted in your sample of 170, right? If many samples of children, 170 children, you calculate the proportion of those children that are nearsighted in each of those samples. If indeed in the population there is 12% of them are nearsighted, and each of those samples of 170 are random samples, independent measurements, then the distribution of those sample proportions should be centered at the 12% or 0.12, normally distributed and centered at 0.12. And this is how we calculate our standard error. And we saw that it's for proportion type data, it's the square root of 0.12, the p, the assumed value given in this question, by 1 minus p over the sample size. The square root of all that, it turns out to, by chance again, it turned out to be 0.025, but you can see it's a very different scenario, but it turned out to be 0.025 again. And so it's often written like this: normally distributed, at least approximately, the mean of all those sample proportions based on sample sizes of 170, it should be 0.12, but the p is actually 0.12 in the population. And this is the measure of the variability of those sample proportions around the 0.12, and it turns out to be 0.025, and that's our standard error. Having all that, then we can construct a sampling distribution by drawing the curve, centering it at 0.12, and marking off 1 standard error, 2 standard errors, or 3, but 2 is enough, in either direction, according to the empirical rule for the normal distribution. And so that gives us a picture of the range of sample proportions you'd expect to get based on sample sizes of 170 children. So therefore, the last question was, how many of the incoming students might the student expect to be nearsighted? If I give a question like that, just go with the 95. Can you say, anyone say, and going with the 95, how many of the incoming students in percentages, again, or proportions or percentages, but turn it into percentages. How many of the incoming students might the school expect to be nearsighted, where there's 170 incoming kindergarten students? How many of them should they expect to be nearsighted, given that in the population there's 12%? In what range of values would you expect? Yeah, exactly. Yeah. So I'm going with the 95. Yeah, so exactly. Thank you. The school should expect to have expect to get somewhere between 7% of the students to be nearsighted, up to 17%. Any questions on that? Again, thank you for turning up and sticking through it.